I am going to introduce our first speaker. His name is Phil Gardner. He is with the USGS. He is a groundwater specialist, and his topic will be the historic development and limitations of perennial yield estimates in Nevada hydrologic basins.
Thanks for that, Ed. I didn't even really think about it when we did this at the conference, but you kind of segued in perfectly. You made me think about where I live in the east side of Carson Valley. Anyway, let's do get the screen share going here. And so welcome to the webinar. And thanks for joining what we hope will be an interesting set of talks. Like Ed mentioned, I'm going to sort of open up this series of 4 talks by giving some historical perspective on the concept of perennial yield, and talk about how it's been used in groundwater management in the state of Nevada, and then discuss some challenges related to groundwater management using the concept. So get into a little bit more of the why behind some of the problems that Ed just highlighted, and then finish with some brief thoughts on strategies for modern sustainable groundwater management. And then the following 3 talks will go into some more detail and discuss some examples, experiences and challenges in Nevada and in our neighboring states of Utah and California. So first, let's start with some formal definitions of what perennial yield is. In Nevada, perennial yield has a specific definition of being the maximum amount of groundwater that can be salvaged each year.
We can't see the slides.
You can't see the slides?
Yeah.
Well, thanks for letting. So yes, like I was saying, perennial yield in the state of Nevada trying to get some stuff out of my way, has the specific definition of being the maximum amount of groundwater, catch up to where I was, that can be salvaged each year over the long term without depleting the groundwater reservoir. So perennial yield is ultimately limited to the maximum amount of natural discharge that can be used for beneficial use, and the perennial yield cannot be more than the natural recharge to a groundwater basin, and in some cases is less. So there's a lot of important points in there that we'll come back to. Similarly, Utah uses a similar concept. They call it safe yield, but safe yield is defined slightly differently as the amount of groundwater that can be withdrawn from a groundwater basin over a period of time without exceeding the long-term recharge of the basin or unreasonably affecting the basin's physical and chemical integrity. So in Western water management, you'll come across a variety of these terms similar to perennial yield, safe yield, basin yield that Ed mentioned, sustainable yield, and in general, they all have the same concept at heart. I mean, basically, they all refer to fixed quantity of water that can safely be removed from an aquifer without causing harm or undesirable effects. But as you noticed in the last 2 definitions between Utah and Nevada, there's some subtle differences, and then that can get interesting when regulating and managing the resource. So there are these perennial yield values that Ed mentioned in his introduction for these basins. So let's talk a little bit about where the values come from. The values are based on groundwater budgets for each basin. The budget being the estimate of the annual amount of groundwater that cycles through a basin's primary aquifer. So these values exist for all of Nevada's 256 hydrographic basins. And the numbers are available on the state engineer's website, along with references to the information where they come from. So there's lots of transparency in this, and it's well known, but there's more, I think. There's a lot of subtlety behind the scenes, the development of them, their certainty or uncertainty, and where they do originate. So we'll start by talking about what the groundwater budgets are in a little bit more detail. Here's a picture of a multi-basin cross-section of a multi-basin aquifer system. and it's showing all the components of the groundwater budget, the ins and the outs. So before pumping begins, under pre-development conditions, only the natural components of the budget need to be included. That's the natural inflow to the aquifer system and outflow from it. So the recharge components of the budget are shown here in green, and they include things like infiltration to the aquifer from precipitation, recharge to the aquifer from stream loss, recharge to the aquifer from seepage, then irrigation return waters, and subsurface inflows from neighboring basins in some cases. The discharge components of the budget are shown in red. And these things include groundwater discharging to streams and springs, usually in low-lying areas of the valley, groundwater discharging by evaporation from moist soils or from plant consumption, which we collectively refer to as evapotranspiration. But once pumping begins in a basin, water levels begin to drop. And then at that point, aquifer storage changes need to be considered. So this is the core of these perennial yield estimates. All the components are measured or estimated through basin scale groundwater resource studies. So next we'll go into a little history on the studies that have generated these numbers. So this slide shows the timeline for the early water resource investigations in Nevada. So beginning back in 1938, Congress appropriated funding for the USGS to cooperate with state agencies across the nation to investigate and better understand the water resources in their states. So with this, in 1944, systematic investigations of the water resources began across the state of Nevada, with Las Vegas Valley being the first area of focus because of its population, and also because it was the first area that noticed a troubling decline in their water levels and flowing wells and artesian pressures that had been their source of water that they relied on. By 1946, the investigations became formalized and started to move across the state. And the reports where these were documented were called the Water Resources Bulletin series of reports. So the series culminated in over 40 reports that documented overall water resource information across the state, often basin by basin, but not completely. 15 years later, there was a little bit more of a groundwater focus. In 1960, the Reconnaissance series of reports began, and this series was initiated to fill gaps in the Bulletin series and specifically to better understand where development opportunities existed across the state, with an emphasis on where groundwater information is limited. And it's worth noting that Utah also, something similar happened, very similar happened there, where the State Division of Water Resources worked with the USGS. And that led to a similar body of work there. They're known as the Technical Publication Series. I used to work in Utah, and we rely on these. And just like they're available here, State Engineer's website, the same goes in Utah. You can find all these historical reports that laid out what was first known about these basins and their groundwater. So together in Nevada, work on the Bulletin and the Reconnaissance series was referred to as the Nevada Groundwater Program. And the groundwater budgets that came from these reports were adopted as the perennial yield numbers. They've been updated in some cases, but these were adopted as the early numbers. And while, as I say, while many basins have undergone updated studies, those values remain for many of the basins. So the motivation is interesting to think about for the early Nevada groundwater program. The initial motivation for the groundwater program really grew out of the timing of two factors. One was the availability of new, cheap hydroelectric power from Hoover Dam. That was completed in 1936, and this power was now available in Nevada. The other was the increasing availability in mid-century of the electric turbine pumps that could be used for irrigation. So together, the two of these presented a big economic opportunity, or what was seen as such, for the state of Nevada, and that was expanding agriculture across the state using groundwater. So expanding agriculture in areas where surface water was fully appropriated already or didn't exist. So by the time this was going on, as I say, surface water resources had been mostly appropriated across the state. So the state of Nevada and the USGS realized that this was an opportunity for assessment of widespread assessment of groundwater availability. And this work would allow farmers and ranchers to invest in locations across the state with less risk, understanding the budgets. And the state was also thinking ahead and knew it would be important to constrain overdevelopment in these basins. But mostly the Nevada groundwater program, which, as I said, was the source of these perennial yield numbers, was initiated to grow the economy and reduce risk to farmers. So now we'll talk a little bit more about how perennial yield has been used in groundwater management since the mid-20th century. So this quote, taken from a state engineer's order, but found commonly in orders and documents related to groundwater rights, sums it up. In Nevada, the perennial yield is the primary guideline used by the state engineer to determine water availability, where the source of supply is groundwater. So what happens is groundwater development in a basin then is typically permitted up to the perennial yield. And the idea being that if this annual replenishment to the aquifer is not exceeded, then groundwater levels after a period of time of initial decline will stabilize. And this has worked in constrained overdevelopment in places throughout the state. But if you remember that part of the definition that emphasizes that perennial yield is limited to the maximum amount of natural discharge, and that can be used for beneficial use. These parts of the definition come from the fact that it was recognized at that time that every drop of water that is going to be pumped from the basin, it's going to reduce discharge from the aquifer that had been going somewhere else. So the fundamental idea in management was that if pumping is permitted up to the rate of natural discharge, then it will capture only the natural discharge and thereby convert the sort of, at the time, thought of as non-beneficial use of water, which would have been going to feed the phreatophytic vegetation in the desert. You can see here in the left diagram, the wide expanse of greasewood. So we convert that non-beneficial use of water to beneficial use of water, irrigation. And it, you can see why this makes sense. And you may or may not have guessed, it also has its limitations. So in thinking about its limitations, let's think for a minute about what happens under an ideal perennial yield groundwater development scenario. So as I said, pumping's permitted up to the natural discharge. And then all the natural discharge is intercepted, groundwater levels stabilize after they begin to decline. But remember, you can't capture all water being lost to evapotranspiration without also depleting the streams that may run through the valley or the springs. And so you suffer these other effects where the vegetation is eliminated, and the spring flows decline or disappear, and the stream base flows decline or disappear. Riparian areas along the stream die off. And this outcome might have been more acceptable at a time when the emphasis leaned toward quantifying groundwater as a resource to maximize for economic benefit. But today, the real challenges of groundwater management is more along the lines of managing for the future and minimizing conflict between users. And the photo here, borrowed from a colleague's presentation here, is kind of a picture depicting an extreme case, when you pump all the groundwater and turn a valley into a dust bowl. So recently I added another image to kind of get this concept across that I think does a more realistic job. So this image here is showing trends in what's called the normalized difference vegetation index. It's just, it comes from Landsat satellite data. And really what it is just a measure, NDVI is a measure of plant health or vigor. And so what's important in this image is that the areas in blue show areas where vegetation has become greener and healthier over the time that the data has been available. And that's from 1984 till present. So since 1984, the areas in blue have grown healthier vegetation, and the areas in red are showing the areas where the vegetation has either declined and become less healthy or died off completely. So the general pattern here really illustrates this perennial yield concept. You can see the areas in blue are big center pivot fields in the south, and then to the north of them are areas that were all the natural vegetation. You can see its decline. And so it's a direct trade-off where the areas in the groundwater has been pumped, applied to areas, grown more vegetation. You can see the natural vegetation has been captured. And so this is the pattern that we talked about that you would expect, but it's not really, it doesn't really show the complete picture, because the problem here is that water levels are declining everywhere, which is the reason for the decline in vegetation. And as that happens, it's also reduced flows in springs here in the center part, more to the north, and ultimately reduced flows to this base flow groundwater fed stream that had typically gone to fill this reservoir. And these springs and this stream and reservoir water had already been appropriated for stock water and for releases to irrigation of areas to the north of the photo. So you can see the problem here. It would have been an ideal perennial yield situation if they had converted this non-beneficial use to beneficial use. But in addition to that, it's impacted existing water rights. So sticking with the theme and summing up some of the limitations briefly, like I just discussed, groundwater and surface water are connected, and that's important, and that has impacts that take you outside of the ideal concept of perennial yield. And this wasn't always as widely recognized as it is today. So in many basins, groundwater discharge is the source to streams and springs and wetlands. And estimates of the perennial yield often include that discharge. So they include unintendedly include waters that are already appropriated. And these streams and springs and areas of gratified vegetation provide critical habitat since they're the areas of important water in the desert. In addition to that, perennial yield estimates are just estimates. They're not exact. So there's always going to have to be some calibrating through the decades afterwards. And these estimates, many of them are based on studies that are 50 to 70 years old. And I guess lastly, the important part is that the true effects of pumping, where the drawdown and capture of this water is going to happen, it does not happen evenly across the basin. The patterns depend on sort of these complex distributions of more and less permeable sediments across the aquifer, and that can lead to unintended consequences. So there's room for improvement to be made in groundwater management, but really it begins with a perspective change from asking how much water is in the system to what are the acceptable changes to the system. After a half century now, it's become apparent that it's not quite as simple as just capturing the non-beneficial use and putting it to beneficial use. There's a lot of other impacts. So instead of just capturing the perennial yield, the intent these days is to ask ahead of time in management, what happens if we do this or do that, and then use that information to make decisions. The figure on the right here is just one example of a tool that helps do this. It's an example of a modern modeling analysis called a capture map, the numerical model used for a capture map. And so what this does is it asks, if I pump at any location in this basin, what fraction of the water will come from the river in some fixed amount of time? So everywhere that's highlighted in that, the idea is if a well was put at any of those locations, then a certain fraction of that water, 100% being the darkest numbers and 5 or 10% being the lightest numbers. But that it's saying that, if a well was placed out here, you know, it would still capture the water that it pumped ultimately would still be sourced. 10% of it would still be sourced from the river. So, you know, with that knowledge, it helps management decision be better informed. And then this is just one example of some of the advancements in data and analytical tools that have developed over recent decades. And then additionally, the question, what are acceptable changes to the system? It's really a societal question that must be answered and asked with stakeholder and public engagement. Since we know that the concept isn't as simple as what originally thought when it was designed. You know, there'll be other impacts. So to best answer the question, information management tools are needed that are based on the best available science. Updated groundwater budgets are needed that should utilize modern technology and methods and include analysis of decades of hydrologic data, or more than a half century of hydrologic data in many cases that didn't exist when the original estimates were made. And of course, they should acknowledge the direct connection between groundwater and surface water in the basins. And finally, tools for management and prediction, you know, need updating. And these include things like improved numerical models and this capture analysis tool that as an example that I showed. And I found that stakeholders that we work with also, you know, really like examples of and ask for, you know, better web-based data visualization and query tools. So it helps everyone be more engaged and understand what is known and about the conditions, the past conditions, and the potential impacts in the basin. And so lastly, I can't stress enough the importance of monitoring and making measurements. The common saying in our field that I think everyone's probably heard is you can't manage what you don't measure, and that is absolutely true. So for real improvements in new and updated management tools, you know, the data are critical. And this includes, as depicted in the images here, measurements of water levels, stream flows and spring flows, precipitation records, evaporation and plant transpiration measurements, and good measurements of what's being pumped out of a basin. And that's a big one that hasn't always been well measured in the past. And lastly, the quality of the models and system prediction tools that are worked on these days are really dependent and made possible because of long-term continuous data sets that they can try to simulate. So more than just making measurements during a study, but setting up programs or plans to, you know, have long-term monitoring measurements made. You know, sustaining groundwater resources in the desert, it's never going to be easy. It's just not much water to go around. But with good data and modern tools and engagement by all the interested parties, I mean, without all those things, it really wouldn't even be practically possible at all. So thanks for joining the webinar. I will not take up much more time and let us get on to hearing some perspectives from the neighboring states and the other speakers. But I first will take some questions if there are any.